Hello, welcome to your lesson on the key points on the graph of a logarithmic curve. Let's begin here. So you will work in Desmos, and on Desmos you will see three graphs: y equals x, y equals log base a of x, and y equals a to the power x. You're going to explore what happens to the graphs as you change the a value. So I'm going to jump into Desmos. I'm going to ask you to jump into the same Desmos window to try some things out. So here is that link on Desmos. Look up here, take that, type in exactly that into your web browser now, and join me in this Desmos graph. Okay, first thing we're going to do is, using Desmos, the Desmos graph, fill in the blanks below. So we're going to find out the domain, range, and asymptotes for different graphs. When a is greater than 1, see, when a is greater than 1. So I'm going to show you that here. I'm going to go in here, there's a slider here. You have your two graphs here, the exponential graph and the logarithmic graph, and you can change the a value. So watch what happens. Right now we don't see anything. We see y equals x, that line of symmetry. But as I make a greater than 1, see, look, I'm making a greater than 1. I'm going to keep sliding this, okay? And you can see what happens. Both graphs emerge, the exponential growth graph and the logarithmic growth graph. So your job then is to do that. Experiment with yours a little bit. Use the slider. Look what happens to the graphs. But again, your goal is to say what is the domain, range, and asymptote. So let's begin with the exponential graph. What are the domain, range, and asymptote? Okay, now look at the logarithmic graph. And when a is greater than 1, what are the domain, range, and asymptote for that one? Okay, let's check our work on that. So here's an example of that again. So I was showing you in the slider already, but here we have an a value of 1.96. We see our exponential growth and our logarithmic. Okay, let's check this out here. So let's check our answers. Here's an exponential growth model. And here's an example of exponential growth, y equals 2 to the power x. We know exponential growth goes like this. Let's begin with the asymptote. Exponential growth always has an asymptote at y equals 0. There's like an invisible wall there. So if there's a wall there, that means our range is limited because y values cannot go below that value. So you can see on the range, it goes from 0 to infinity. Y values can be anything from 0 up to infinity, forever going up. So y values are greater than 0. The domain, however, can be any x value because this graph will go forever in this direction and forever in this direction. So x values can be anything from negative infinity to infinity. In other words, x value is an element of the real number set. It can be any real number. Let's look at the logarithmic growth here. An example of that is log base 3 of x. Okay, so it always takes on this shape. You can see right away that it's the inverse of the exponential growth. Logs and exponentials are inverses of one another. And if they are inverses, the asymptote, which used to be y equals 0 here, is now x equals 0 here because the x and y values have been swapped. So we have an asymptote here. So there's a wall here, and that wall restricts the domain because x values cannot be below that value. So we can see our asymptote is x equals 0, and our domain is from 0 to infinity. Okay, x values begin at 0, go to infinity, or x values are greater than 0. The range, however, is unrestricted. This goes forever down, and this goes forever up. Therefore, negative infinity to infinity, or y values are elements of the real number set. All right, let's switch things up now a little bit. Same exercise, you're going to use the same Desmos activity there, but this time you're looking at a values that are between 0 and 1. Look, a values between 0 and 1. In other words, what happens when you make the a value, the base of the exponent or the base of the log, what happens when you make that a decimal number between 0 and 1? So let's check that out. Experiment in Desmos. Let me go back there. So now I'm going to take my slider and I'm going to make the values of a between 0 and 1. All right, right away I'm going to see the graphs have changed. Okay, that's what they kind of look like. So experiment with that in your own Desmos window and then describe what's happening. Is it still growth? What's going on? What are the domain, range, and asymptote of the exponential model in this case? Okay, and now what are the domain, range, and asymptote of the logarithmic model when a is between 0 and 1? Okay, let's check our work. So again, here's an example of that. I have an a value of 0.5, 1/2. That's between 0 and 1. And look what happened. The exponential growth which is this purple one, became exponential decay. And we know that. We've talked about that a lot. When a becomes a decimal value, this becomes decay. And the reason for that is, imagine 0.5 was put in here. 0.5 is like a half. So if you had a half here, that's decay. But also a half, if you want to bring the 2 up in that fraction, it's 2 to the negative 1. So we have 2 to the negative 1, or 2 to the negative x. And when we make the x negative, that is a reflection over the y-axis. And that's what happened. It used to be exponential growth, and now it reflected. We've talked about that a lot. But look what happens with the log graph as well. So here's the log graph. A normal log graph goes from the bottom and then flattens out. From the bottom, flattens out. This one is a reflection of that. But this time the reflection is over the x-axis, all right? So the exponential one reflected over the y-axis, and the logarithmic one reflected over the x-axis, because they're inverses, right? So the inverse reflection took place, and that's what we see on the graph here. Really important to think about it that way. Okay, let's check all the details here. We are looking for domain, range, and asymptote. Here's exponential growth, in this case decay, because a value is between 0 and 1, so we can see decay. The asymptote remains at y equals 0. The domain is still negative infinity, positive infinity, and the range is still from 0 to infinity. So check all that out here. Now let's look at the logarithmic model with a base that is a value between 0 and 1. So I have 0.4 here. Looks like this. Again, that's a reflection over the x-axis, whereas this one was a reflection over the y-axis, right? So it goes down now like this. Here's our asymptote, remains the same. Here's our domain, still restricted from 0 to infinity. And our range is all possible values, negative infinity to positive. Pause there if you need to. Contemplate that a little bit more. Okay, let's keep moving forward. Now, we are going to look only at the graph of y equals log base a of x. So let me go to Desmos there. I'm going to hide my exponential growth. We want to look at only this one here. I'm going to make this a normal log graph like that. I'm even going to get rid of the reflection line here. So we're looking at only the graph of log right here. Okay, the log function. Now, looking at only that graph, we're going to notice what happens to 2 key points on the graph. And the 2 key points are labeled in Desmos. We're going to enable those right now. So go in your Desmos window. Here are the 2 key points. Here, label that, go that, click label, label. You should see 2 key points. All right, now I want you to observe what happens to those 2 key points as you slide the a value. What happens when you change a? What happens to those 2 key points? So kind of watch what happens to them. Think carefully about the values. Notice the 1, 0, 1 just gets locked there, right? That's the one key point we always talk about. 1, 0 always seems to remain there. However, and what's the reason for that, right? When you put 1 in for x, that means here you're thinking a to some power equals 1. And the only way we can get something to some power equaling 1 is if it's 0. So 1, 0 is that point for sure. That one's locked. But look at the other point. Look at the other point carefully. What happens? Oops. All right. What happens to the other key point? Well, it seems to move along the curve, but look at the values of it. The y value seems to remain at a 1, but look at the x value. What do you notice there? Well, the x value of that key point is the same as the base. We've said, look, the base of the log is 3.5 here, and we can see there's a point 3.51. Now I'm going to change the base of the log. Look, the base of the log is 4.5, and now we still, look, 4.5 here, and we have a point 4.51. So why does that happen? Why do we have this point that has the base of the log in 1? Well, let's think about it again. So you put in, let's make this 5. Okay, a is 5. So now we're thinking 5 to some power equals, and we see there's a 1 here. So that x is replaced with a 5, and we also have a 5 here for our base value. So 5 to what power equals 5? Well, it can only be 5 to the 1 power, so y must be 1. Okay, think about that for a moment. Those are called 2 key points on a log graph. So let's go back to here. Our 2 key points are 1, 0, and a1. We can see it here. 1, 0, and a1. So that's what we have here. When we have a log graph, the 2 key points are 1, 0, and a1, the base of the log in 1. And also on that logarithmic decay, That means when a is between 0 and 1, it's the same thing. A1, 1, 0. Same two key points. Okay, let's keep going from there. We're going to apply this idea. So here's the two key points on a log graph, 1, 0 and A1, A being the base, right? Look at these two graphs here. Again, we have log base 2 of x. So we can see 1, 0 is on that graph, but also 2, base of the log 1 is on that graph. Now let's look at this logarithmic decay. 0.5 is our base, so that's why it's decay. Remember, when this value is between 0 and 1, it becomes logarithmic decay. And we see 1, 0 is on that graph, and also base value 0.5, 1 is on that graph. Pause here and just make sure you can memorize those two key points, how that works, all right? Let's go to the next thing. We're going to try some practice problems using that very idea we just discovered about the log graphs, the two key points. So here we have 3 log equations and 3 graphs. Your job is to match an equation to the graph. Okay, we can clearly see each of the graphs passes through 1, 0 right here, but look for the other point. The base of the log and 1 is the other key point, so that should help you do the matching. Try it now. All right, first thing you could have noticed was that we have, okay, so here's all the key points. And the first thing you could have noticed is this log here has a base that's between 0 and 1. Therefore, that's going to be logarithmic decay, like this, right? Whereas the other two log equations have values that are greater than 1 for the base. That means they're going to be a normal log graph like that, logarithmic growth. Okay, so that one is this one, because we can see the point 2, 1 on there, so the base 2 and 1. This one here is going to be here, because we can see the point 5, 1. The base is 5, and finally here the logarithmic decay, and we see the base of 0.3, and that point is 0.31 right there. Great, that's how we can use those properties to find graphs matching to their equations. Let's try another one. So here's one here. Again, we have 3 graphs. Your job is to state the domain and range for each, and then state the base of the logarithmic equations. So if you were to write each of these in this form, what would that a value, the base number for each of these 3 be? Try a. Okay, let's check our work for a. We have this domain, we have this range, and we have a point there at 3, 1. Therefore, the base must be 3, so that a value is 3. Great, try the next one. This is logarithmic decay. The domain is this, the range is this, and we have a point right here, 0.5, 1. So the base must be 0.5, so a value 0.5 for this one. And last one. Okay, domain, range, and our point at 1, y is 1, is 0.5 for the x. So 0.5 is our base. Sorry, not 0.5, that's not right. It should be 5. So a equals 5. Ignore that. That should say 5. And look at that. Just like magic, it does say 5. All right, great. So I hope those ideas are solid in your brain. And let's move on to an applied problem now. We have this situation where this data in this table is showing the height in meters of a silver maple tree measured at the end of each year. And we can see here's the age, okay, end of year 1, end of year 2, end of year 3, and so on. And here's the height in meters. So clearly the tree is getting taller, but how much and at what rate? And can we make a function to model that? Let's check it out. Plot these values on the graph and estimate a value of a. So let's say you take all these data points, put them on this graph here, or on this coordinate plane, and then you'll see a shape that kind of looks like a log graph, I think. And then your job will be to look at that graph and estimate the value of a. So again, remember that the point A1 is always on every log graph. So what would that value of a be if this was modeled using a log graph? Try it now. Okay, so here's all those points plotted. They definitely follow a logarithmic growth curve like that. And we can see if we connect those, that when you look for the point y value of 1, it is right here. It is about 1.2 on the x-axis. So that means the base of the log must be 1.2. So here's what the log graph must look like. Again, the base value is the x value when y is 1. Okay, let's remind ourselves of why that point works like that. It's important to really understand that. When I put 1.2 here, and then I have a point here with x value of 1.2, so if x was 1.2, we would say 1.2 to what power makes 1.2? And it would be 1.2 to a power, which means a y value of 1. All right, so we just saw how you can plot the points, sketch the curve through them, and then approximate the value of the base of the log by taking a look at where the y value is 1 and what the x value is at that point. However, you might be thinking, well, that's kind of an approximation because maybe you drew a curve slightly differently than this, and maybe you got like 1.3 or something, and you don't agree with this. So let's look at the algebraic way to also find this rather than just approximating from the curve. So you can take any of the points, or data points, right? So I'm taking the data point 3, 6, which is right here. And I'm going to say, well, let's say the curve passes through that point. So 3, 6, I'm going to put my basic log model here, and I'm going to substitute the point 3, 6 into it to solve for a. So 6 is our y value, and 3 is our x value for that point. And now I can use this to solve for a, right? I can change this into exponential form, first of all. So a to the 6th power equals 3. And now that I have this exponential form, I can get rid of this power of 6 by taking either the 6th root on both sides, or alternatively, you can apply an exponent to get rid of this 6 here, right? If we apply an exponent of 1 over 6 to here, and then we do the same thing on this side, that 1 over 6 and the 6 here will cancel, become a to the 1, which is just a, right? So a equals, and 3 to the 1/6 power, turns out it's 1.2. So now I want you to try the same. Let's take another point. Let's say you had chosen a different point. For example, the point 8 and 11.5. So try the same process with 8 and 11.5 and see what value you get for a if you use those points to approximate it. Okay, let's check. So it's not always going to be exactly 1.2, right? Because not every point is going to be exactly on the curve we're creating, but let's try. So 11.5 and 8. Follow the same process, a to that power equals 8, and then you apply that reciprocal power here to get rid of that 11.5. 8 to the 1 over 11.5 power is close to 1.2, but not quite. So anyway, that gives you an idea of, you could have taken any any points and put the x and y into our log form to see what the equation would be to model this. All right, so we've done good modeling with exponential curves and now log curves. Good question. Let's keep this one going. There's a few more questions to look at. So find the inverse of the function and then state the domain and range. So again, here's the function we just created. Find the inverse, state its domain and range. Okay, so the inverse, we swap the x and y values. We change to exponential form. And well, that's our inverse. So our inverse is this exponential function. And the domain and range of any exponential growth function, which this is, well, the domain is all real numbers, and the range is y values from 0 to infinity, because we know there's an asymptote at y equals 0. Okay, next, confirm graphically that the inverse, that the function we have here is the inverse of the original. Well, if you graph these on Desmos or on your calculator, if it's a graphing calculator, here's our, in blue is the log base 1.2 function, and here is our inverse that we just found, 1.2 to the x power. And you can see clearly from this graph that they are definitely inverses. They are mirror images across the line y equals x. All right, next. Okay, let's do one more thing to wrap up this problem. And the last step we're going to take is this. So it says, using the original function, which is the log one here, approximate the height at 5.2 years. Okay, so that means just putting 5.2 into the function, right? Because that original log function represents this data. So our x values are the years, our inputs, and our y values are the height. So let's figure it out. Here's our log function. We are going to input 5.2 years in there as the input, and we're going to find out the height y. That works out to 9.04 meters. Let's see if that makes sense on our graph. At 5.2 years, so it's 2 years, 4 years, 5 years is about here, 5.2, and then I'm going to go up to here. Yep, looks like about a height of 9 meters. Makes sense. Now, it says using the inverse function, approximate the age when the height is 7.4. So now notice we're looking for the age of the tree, and we know the height. So of course we could use the original function and just put 6.4 in for y, because that's the height. But if you remember, in our recent lesson we talked about this. What is the purpose of an inverse function? An inverse function takes some original function and swaps the x and y values, right? So if we swap the x and y values here, all of a sudden it is the x thing that we are solving for, and that's what the inverse will do here. So apply the inverse to find the age when the height is 6.4. So here is the inverse function. We're going to put in, for the input now, since we've swapped x and y values, now the inputs are the heights, and the outputs are the years. So we put input the height, and we can calculate that to get the height. Or sorry, yeah, no, the year at which that will happen. So again, inverse functions allow us to do the inverse operation where we swap the inputs and outputs. So that's the power of an inverse function. All right, great job, and we'll see you soon.